Hello everyone. In this tutorial I'm going to show you how to use the software Wavenology to create a simple square patch antenna. Eventually the case will be like this. I'll start from the beginning and go through all the details you need to know. So let's take a look at this new project. This is the empty environment. So to begin with, you need to start from the design process. You can double click any buttons here and it will show up a window. Basically it's asking you all the basic input informations. So for example, the first thing is unit. You need to know the time unit, frequency, and length. And then the background, in this case will be air. And also the boundary conditions. You have all kinds of boundary conditions as listed here. PEC, PMC, periodic, and things like that. And you can also, in this case, I know along Z direction, so I need to have -3 millimeters, and top is only 30 millimeters. And click apply, you will see the domain is automatically adjusted. Next is the frequency range. So in this case, I'm interested in only 1 gigahertz to 2 gigahertz. And click apply, and you can also take a look at the transient pulse that is going to be used to excite the structure. Next thing will be the mesh. Typically we choose 20 points per wavelength, and the advanced features you don't have to worry about that at this point. The last thing is for transient simulation, you need to tell the solver when to stop. Typically you can choose automatic. This will have two criteria to determine. One is energy decay, the other is energy variation. So this is a dB. You can select higher and strict standards. This is for the result, to how fine is the resolution of your result you want to see. In this case I choose 5 for this, and then I click OK. That's basically all the information you need to put in. So the next step will be drawing the geometries. In this case will be 3 boxes only. In this case, first let's draw the ground. Let's name the geometry as ground. And then the corner, I know the dimension already. I'll just directly input them. 40, 40 to 1. And material is PEC. So you fit into the window, you look into the ground plane. The next thing on top of it is the material, that is a substrate. So you name it as substrate. And then material is not here, you can create it. The material name, let's say whatever, PCB. You can also change the color. And then here is the input to edit this material. In this case it's simple enough. I just put a relative permittivity to be 4.24. You can also edit the dispersion. You have all kinds of dispersion material types, but in this case we don't need that. So just click OK and enter the dimension. Again, it starts from 0, and thickness is 1 point. Okay, so you can see, okay, it's the substrate is there. Next thing you need to draw is the patch antenna. The material is PEC now, and name it as patch. And again, I know the dimension is -23.75. Of course, you start from on top of the substrate. And you want a thickness to be 1 millimeter only for the PEC substrate. Okay. Now you see this geometry is there. So that's basically the geometry creation. The next thing you need to do is to set up the source. In this case, we use a lumped source right beneath the patch to excite the structure. So here you can select lump port, create, and it's asking you to select 2 points, start, end. In this case you can just double click here and you see it recognizes your coordinate, but of course it's not accurate, so you need to set a position manually on your own as well. Say 4, -4, and minus 0.5 millimeters along Z direction. and here you can say for -4 and 2, and then the lump port is there. Of course you cannot see it clearly. I can change the transparency of the geometry so that you can take a look. Double click as well and then make it transparent. Now you can see the lump port is buried there in the substrate. Okay? One thing you need to make sure is the lump port is touching the two metals. So when you enter the coordinates, make sure it's penetrating into the metal, at least a little bit. Okay? So that's the structure. And now you can start to run your simulation, but before you do that, you need to tell the solver what kind of results you want to take a look. So the most common thing is the field. So we have few observers here, and the window you can set up where the location of the observers you want. In this case, let's say -20 to 20. The nice feature about this, you can do array creation. Along which direction? For example, direction 1. Along X direction, step is 10 millimeters, and I want 5 of them. The other is along Y direction, I want 5 of them as well. So you can see all the observers are created, and they're plotted in the 3D canvas as well. Okay. So the next thing you want to take a look as well is, since this is antenna, you want to see the surface current. So first thing we can take a look is the field, electric field, on a face cut. In this example, let's say we want to take a look at the field at X plane. So you need to enter where is the plane. Okay. According to the information here, the bounding box size, you can know that, okay, I want 0, -56, -3, 0, 56, 30. So it covers all the entire region. You can take a look, it's defined like this way. Okay, all the field will be shown there. The other thing you can take a look is you can select the object, for example the patch, right click, it has the menu here, create snapshot for electric current on solid. Create that. It will also be recorded as a result. And for antenna, there's another feature, is the far field. So you can create a regular far field, and the frequency is just 1.5 gigahertz, that's fine, and create. This will be recorded as a result as well. And that's basically it. You can just start to run the simulation. As you can see, there's all kinds of informations here, statistics, number of cells, and the CPUs, and also the time steps needed, times elapsed, and how many times it remains. So as simple as that. Okay, see, this is very fast progress bar. So to save some time, I'll just stop the simulation and then directly go to the finished one already, the result. This is identical to the last design. We just take a look at the result. So the results is all here. First of all, you can take a look at the field, EX field. You can take a look at, it's resonating at one frequency. Okay, and also you can also edit the title here. You can zoom in and zoom out the labels here as well. Okay, and you can also move the axis up and down. So this is a 2D canvas. That's the field observer. The other interesting thing is all the transient data have the frequency domain response as well. So if you take a look, you can see that the signal is FFT'd, and you can see the resonant frequency is right at 1.5 gigahertz around. The next thing you can take a look is the S parameters through the lump port. You want to know the reflection coefficient of this antenna. As you can see, at 1.45 gigahertz, the energy radiates out. And you have other options, the real part phase and the imaginary part as well for S parameter. And input impedance, you can also take a look. As you can see, it's at the same frequency, the real imaginary part as well. So this is another important parameters. And of course, scattered voltage and transient and frequency domain. You can also take a look at them. And the snapshot you're ready to see is let's say, first let's take a look at the surface current on the patch. So you can move it over here. I want to hide the field vector. You want to use log scale to make the small colors more obvious to see. And you can see it's resonating and begin to radiate out. You can make movies, you can make export the images as whichever way you want. And you can also take a look at the face snapshot as well. So for example, it's over here. You have preset views like this way. I want to choose log again. And you can see the field is coming out and it's radiating out. Transient domain. Okay. So this is how the snapshot is going to look like. And then the last thing is we define the far field. You right click, just display, and you can see that the radiation pattern is like this. All the energy is reflected by the PC ground. There's a little thing on the other side, but mostly going to the Z plus direction. You can also use the log scale to view it more obviously as well. Okay, and this has all the other things like the gain, efficiency, directivity, and things like radiation power are all calculated as well. So basically that's it, as simple as that. You can also define more complicated structures and on other systems, scatterings, and things like that. But we will cover that in the future tutorials. Alright, thank you very much.